Electrodynamics is usually described in great confidence as if it's been solved years ago by the great minds of the physicists like Maxwell, Einstein, and Feynman. But not everybody remembers that even they pointed at failures of the existing model, failures that haven't been resolved yet. When calculating a charged particle's energy and momentum using Minkowski's energy-momentum tensor, the entire energy of the electric field is the sum over the volume surrounding the particle. As long as the particle is not moving, there will be no problem. But a paradox arises when trying to calculate the energy and momentum of a moving charged particle. Before movement started, beta was zero and the magnetic field was null. But after movement started, beta is no longer zero, therefore the magnetic field is greater than zero. When using Lorentz transformation, there is an added term in the electromagnetic energy and momentum calculation, which gives this. And the momentum is this. But according to Einstein, the momentum should be this. The particle's mass comes out greater by a third from the original stationary electromagnetic mass. That's indeed strange. Abrams and Lorentz noticed something strange. Let's take a neutral particle and a charged particle. The mass of a neutral particle is the mechanical mass, and the mass of a charged particle is comprised of the bare mass of the particle with the mass of the electron charge that was added and the mass of the electromagnetic field that has been created. When accelerating a neutral particle and a charged particle with the exact same total mass using the same force for the same distance, both particles will gain the same kinetic energy. But how could that be? An accelerated charged particle radiates energy that the neutral particle does not. This additional energy had to come from somewhere. To solve this weirdness, Abrams and Lorentz used Newton's equations and inserted the force of L'Amour radiation term. But Abraham-Lorentz equations created a new problem, a paradox. According to the new equations, charged particles emit radiation that creates a self-force on the particle and accelerates it. But if we look at the equation closely, we see that the integral extends from the present to infinity far in the future. Thus, future values of the force affect the acceleration of the particle in the present. In other words, this acceleration of the particle happens prior to the application of the force that is accelerating it. Now that's just unphysical, isn't it? We have only talked about a few paradoxes in classical electrodynamics, but there are more. It shows how incomplete our model of nature is. Feynman said, the classical theory of electromagnetism is an unsatisfactory theory all by itself. There are difficulties associated with the ideas of Maxwell's theory which are not solved by quantum mechanics. Furthermore, the difficulties do not disappear in quantum electrodynamics, which are associated with the concept of electromagnetic momentum and energy. A theoretical physicist, Doron Weinfeld, also assumes that the problem lies within the basic assumptions of classical electrodynamics, which are missing a key component, the inertia of the electromagnetic fields. Could this be the solution to end all paradoxes? Check out our next video or read the complete article to learn more.